And last up is Liz Chamberlain, and her title is Using OSL and Carbon-14 Dating to Reconstruct Mississippi Delta Evolution and Carbon Burial.
Right. And here we see one of the ways that we do that. We're moving onshore a bit now into the subaerial delta and its marshes and looking into the substrate. And we do this mainly with coring. So here a vibrocore that's going down into the delta sediments and recovering what's there and what's built the delta. The river has moved with time in this delta and many others as well. Here we see a map of that. For the past 1,000 years or so, it's taken the present day course that we can see today. Prior to that, the river came down this blue course, the Lafourche subdelta, and it built a large area of land, over 6,000 square kilometers. Every time the river has moved to a new location, it builds new land there. And we can look at that building process by looking into these substrate with the cores. In general, what we see is a very clastic rich record, lots of sand, lots of mud. This is a general schematic showing the river building out, building new land. And the red represents sand here, yellow is silt, green is finer grained mud. And so this is something we see when we look into these old delta archives. This is showing the real data in a cross section from upstream on the left to downstream on the right. This is along Bayou Lafourche, one of the past pathways. And what I want you to notice from this figure, again, red is sand, yellow silt, green is mud, brown is peat. That's our organic rich units. It's really, really clastic rich. Lots of sand, lots of mud. We've also managed to date it using OSL dating, which I'll talk about in a minute, and radiocarbon dating. And these are our ages in 1,000 years. So for example, this would be about 1,500 years old. These are the radiocarbon ages here. And so lots of sand and mud here. And when we look into the rates that we get from these ages, we see that the clastics, the sand and mud, deposit very fast. In this case, more than 8 meters of aggradation building up over less than 1,000 years. The peat is much slower. You can see here it's bracketed by 2 ages at the top and the bottom of this unit, which has been compressed, but it's less than 3 meters over more than 4,000 years. The amount of peat versus clastic material can really vary in systems. So the Rhine-Meuse Delta in the Netherlands, where I live now, is much more peat rich than the Mississippi Delta. And the Ganges-Brahmaputra Delta is very clastic rich, very sandy. In general, we see that this is a function of the sediment yield of the system. So how much sediment is washing down to the delta per unit area of the delta per time. And in high sediment yield deltas like the Ganges-Brahmaputra deltas, there's just so much more sand available to fill the accommodation that is created by relative sea level rise, by sea level rise and subsidence. And because the sand and clay deposit so much faster than the peat, they're more efficient at filling the accommodation that's created. And so in these high sediment yield deltas, we get very sandy records and less peat. This also influences the type of methods we use to date these. So in the Rhine-Meuse, radiocarbon is very widely used for dating. And in the Ganges-Brahmaputra, it's largely OSL. And in the Mississippi Delta here, it's somewhere in between. We can do a bit of both. Very briefly, OSL dating dates the deposition of sediment based on a signal that's sensitive to light exposure. This is a method I specialize in, and I'm happy to talk about it more later. We perform the dating in a darkroom like you see here. This is at the Netherlands Center for Luminescence Dating where I work. And in contrast, radiocarbon dating directly dates organic material. So this is widely used for dating peats and other organics in deltas. Thinking a bit about the conversations we had yesterday, integrating across space and time scales, we have all these different methods available to study deltas. This is graphing them with the age range, how far back in time they go, versus the resolution, what resolution of processes they can get. And then looking at that plotted here, ranging from very short-term processes like floods, storms, tides, and seasonal events, up to human land use change, river channel migration, and then the longer time scale, avulsion, delta lobe dynamics. When we can use these different methods to interrogate a system, we get a more complete view of its dynamics. So OSL and radiocarbon contribute to that by dating these longer time scale processes, which plot here on our diagram. So this is a task to add them later. All right, to move into some examples, in the last couple of years, I've gotten to come here several times for work and work on some really nice projects with Carol Wilson and others based in Louisiana. And in these, we're looking at the wetlands, the delta deposits, the way that these systems have evolved over time and their capacity to sequester carbon. I'll show a couple examples really quickly to these projects. I've contributed to the geomorphic reconstructions and the dating, and other experts have done the carbon work. So one of them is Dr. Kelly Sanks, who could not be here today, but she would be an excellent person to explain the carbon aspect of this work more. We've looked into one of the sediment sequences where the delta was building here. Here's our sand at the base. It's dated with OSL, and Kelly measured the carbon that's stored in these deposits. And what we're seeing from her work is that because sands deposit so fast, they store a lot of carbon quickly. So it's the rate of carbon sequestration in these sandy units can be very high, just because the sands themselves deposit so fast. We're seeing a similar thing here at the Myrtle Grove diversion site, where we have a very long core that goes down more than 35 meters. You can see it here, and it penetrates into the Pleistocene sediments. So it's capturing open shelf pro-delta deposits, deltaic marine front, the sandy mouthbar units, and then some of the subaerial delta deposits as well. And this is a PhD student, Jord, who's at Utrecht University, working with Torbjörn Tornquist and others to look at the carbon sequestration rate in these sediments. And most recently, I worked on a project that Carol Wilson led, looking at these questions in Barataria Bay. So this is some work that was produced by Carol's master's student, Mike Pierkowski at LSU. Here's Mike over here. And we did a series of boreholes into the receiving basin of the Mid-Barataria diversion. And these are some of his preliminary results, again, with OSL and radiocarbon dating. We don't have the answer yet for how the carbon sequestration looks here, but it'll be interesting to see again if we see this relatively high rate of sequestration in the clastic deposits. So in the subaerial delta, it's wetlands and the sediments that underlie it. We're seeing that peats, of course, are organic rich, but like Tracy pointed out yesterday, they grow very slowly. And in contrast, clastics are organic poor, but they're fast to form. And so this means that we can see a greater rate of organic carbon sequestration in clastic sediments, even though the concentration is much lower. And this is what we're observing in these studies in the Mississippi Delta. And so when you take it and think about other systems like the Ganges-Brahmaputra Delta here, where this is a figure that was provided by Steve Goodbread showing 90 meters of largely sand deposits through the Holocene here. And this is a very large delta as well. And I'm very curious about what type of carbon sequestration happens in a system like this. Thank you.